Okay, so unfortunately it seems like the Zoom recording didn't take, or it's not in a format that we're able to open and use. So I don't want folks in particular that actually attended the lecture, and it did say 6 p.m. My intention is always going to be to start at 5:30, just stick to our regular class time. I don't know why it was set at 6. Maybe it was just a default setting in the Zoom app. But what we're doing here in Chapter 6 is one concept, but it's applied to really 3 different scenarios. But it's the idea of a confidence interval. So the overall concept of a confidence interval is we take a estimate. Let me try that again. We're going to have some kind of estimate. Maybe it's a mean or it's a proportion. And then the idea is we're adding and subtracting a margin of error to that estimate. The way that we get that margin of error is with some critical value. And that's based on our confidence level. If I want 95% confidence, then I'm going to need a larger margin of error than if I had 90% confidence, right? If you're 90% confident of making a shot in a basket, and I make the basket bigger, you could be more confident. So a higher confidence level is generally a wider interval. Okay, and then we multiply this by our standard error. Okay, and this is what we focused on in our class last week. This is your central limit theorem, that when we take a sample of a particular sample size, those estimates tend to get closer and closer to the mean. So I apply this 3 different ways. In 6.1, I take x bar as my estimate, add and subtract. My critical value is from the z distribution, and I multiply by sigma x over root n. That formula shouldn't be too unfamiliar. So that's what we do in 6.1. In 6.2, we're still doing means. So our estimate is still x bar, except we look at, and this is really what we would use more in practice, the t distribution. Because we don't have the population standard deviation, we have sample standard deviation. Okay? And then finally in 6.3, we're estimating proportions. This is what you see in elections and polls all the time. And we go back to the z distribution again. So that makes that a little bit easier. But your formula is a little bit different. It's p hat times, this is q hat, or we could just say 1 minus p hat. That's usually how I like to write it, over n. So your textbook authors are going to put q hat there, but every time I do that, my students always say, well, where'd you get that number from? You just subtract from 1, okay? And then the chi-squared interval is going to look a little bit different from this, so we'll cross that bridge when we get to it. That's a different type of distribution that we use to estimate variances, but really you can see this is the same concept over and over again. It's a confidence interval. We're adding, subtracting a margin of error, okay? So let's jump to some examples like what we did in class and see some of this fleshed out or in practice. So this is the t distribution. Let me start off more simple with the z distribution. All right. So in 6.1, we are saying that sigma, the population standard deviation, is known. Generally, this is really not the case. It's not real practical to be able to work this way. But for our intents and purposes, we'll do that for 6.1. I think it's an easier way to introduce to the topic of a confidence interval. So our first example, we have a random sample of 40 student athletes, and we have the 40 numbers listed here. So if you were going to take on a problem like this to make a confidence interval, of course you'd want to put these 40 numbers either into your computer or into your calculator. If you remember, you would go to Stat and Edit, and you can put your list of 40 numbers in there. For the sake of doing the example here, we're not going to need to do that, but your one variable stats could get you your mean, 21.1, okay? And then we have a standard deviation that would be associated with that, okay? So a level of confidence simply means this. This is what is hard for people to picture sometimes. You have your parameter out there in the population, and generally we don't know what it is. What are we trying to do? We're trying to estimate it, okay? So I have all these x bars, all these estimates, and I can go into that population and grab an x bar, and I build the interval around it, right? I take x bar plus or minus, so maybe I get an x bar out here. But when I add the margin of error and subtract the margin of error, notice that the interval contains the mu. Maybe I get an x bar over here, okay? And then again, the interval contains mu. Now we know, if suppose we want 95% confidence, well, I'm building a margin of error off of that where this is 0.025 in this tail, and this is 0.025 in this tail. So 5% of the x bars that I get, it's not going to be very often, but there's a chance that I get an x bar out here or an x bar out here, and when I add and subtract the margin of error to it, it doesn't capture the true mean. Okay, that's the idea of the confidence level. As your confidence level goes up, the intervals get wider. You add and subtract larger margin of errors to them. Okay, so that's what we're unpacking here. If I have a 90% confidence interval, then I've got 5% in each of these tails, and I have to be aware of that. How do I get this critical value for 95% confidence, right? In other words, we're saying, or 90% confidence. If I know that we have 90% in here, how would I figure out what that z critical is? And the easiest way to do that is to use your calculator. We've done this before. I would use second, let's quit out of here, second and the variables key, and I'm going to use inverse norm here. We can also use inverse t in the later section, but remember how this works. It's always area to the left. So I got two things I could put in. What's my areas to the left here, right? Well, if there's 5% in this tail and 5% in this tail, right? Then if I wanted this guy, the area to the left is 95%, right? It's 90 plus this 5%. So I could inverse norm 95%, or I could inverse norm 5%. You're going to see you get the same number, just a different sign on it each time. So if I were to inverse norm 0.95, and the mean is 0, it's a standard normal z distribution, okay, I get positive 1.645. So that's where that 1.645 number comes from. If the z-score is 1.645, then it's at the 95th percentile, basically. Now if I use my little second enter trick, let's change the 0.95 to 0.05. And we get negative 1.645. Okay, so that's how we will get those critical values if we need to look those up or we need to get them. Just use inverse norm. I think that's the easiest way to get to it. All right, so let's look at one in practice here. Use the data from example 1 and a 95% confidence level to find the margin of error for the mean number of hours spent on required athletic activities. So if I know the population standard deviation is 2.3, okay, and my sample size was 20, okay, we want 95% confidence level, okay, so we could use our calculator, inverse norm 0.975, right? If this is 95% inside here, there's 2.5 here. So we get that critical value first. It's 1.96 or negative 1.96, okay? So how do I get the margin of error? Okay, remember what your margin of error is. It's what you add and subtract to x bar. So you have this plus or minus z critical sigma x over root n, okay? That's my margin of error, okay? So my z critical value is 1.96. Standard deviation, they just give that to me here. It is 2.3. And then the sample size was 20. So now it's just a calculator deal. You just plug in 1.96 times 2.3 over root 20. Okay? So that's how we would go about getting our margin of error, just the margin of error. Now how do I get the confidence interval? Well, the confidence interval is just we add and subtract the margin of error. So I would have 21.1, if we get to that. All right, I take the point estimate of 21.1, that was the average of the 40 values, and I subtract 0.7 from it, and I add 0.7 to it, and then this is my confidence interval. Okay. I want to look at what this looks like on your calculator, right? So we're going to do that. We won't do example 1. Let's get to a different example, right? Okay, so a college admissions director wishes to estimate the mean age of all students currently enrolled in a random sample of 20 students. The mean age is found to be 22.9. From past studies, the standard deviation is known to be. So when we see this, we know we're going to use this z interval. Construct a 90% confidence interval for the population mean age. So this is how simple we will make this. You're going to go to stat, and now we're going over to tests. The one menu we really haven't started to dive into yet, right? And in 6.1, we are doing Z intervals. In 6.2, we're doing T intervals. As I kind of laid this out for you when we started this off here. So 6.1 on the calculator, we're talking about Z intervals. We're doing confidence intervals for means using the Z distribution. In 6.2, it will be the T interval. Don't really need the T star there. Okay. And then in 6.3, when we do proportions, this is a 1 proportion Z interval. Okay, it's going to be real helpful to you to know your way around the calculator on these. So we want the number 7, the Z interval. All right, and you notice what it asks for. You'll notice this right away. It asks you for sigma, so you'll know whether you hit the right interval or not. So it says your population standard deviation, that's the kind of the giveaway here, is known to be 1.5. So I put in 1.5 there. The sample mean was 20. Let me check it again. 22.9. The sample size was not 800. I think it was 20, right? Yep, at 20 students. Pretty small sample size, but since the population is normally distributed and we know standard deviation, we can do that. And we want a 90% confidence level, not 99. Okay, so all of those things you're going to have to just grab from the narrative when they give that to you. I'm going to press enter, and I get 22.348 to 23.452. Here they're working through all the nuts and bolts to it, get the margin of error, add and subtract it, but we get the same answer pretty quickly, 22.3 to 23.5, same answer. Okay, and we use the calculator for that. All right. The other thing that I want to talk about with confidence intervals is this question of finding a minimum sample size. So there's one of two ways you can do this. You can just lean on this formula and dump right back into it. I'm going to set up the equation based on the same formula, but then I'm just going to kind of walk you through the algebra of how we would go about solving for n rather than just plugging into that equation. But you're welcome to, if you just have that equation in front of you, trying to find sample size, just plug everything into it, right? You're going to have the confidence level. For 95%, it's 1.96. For 90%, it's 1.645, where you go look it up accordingly. The margin of error is going to be prefixed. They're going to tell us we want it to be such and such, and they'll give us sigma. So we could just plug into all of those. All right, so I want my so this is back to example 1. So we have to remember from example 1 that the standard deviation they gave us was 2.3. Okay, so when we think about this, we want the margin of error to be no more than half an hour, right? 0.5. So when I calculate that margin of error, I say it has to be 0.5, no greater than that. I don't mind if it's smaller than 0.5, that's fine. But so the margin of error is constructed by taking 1.96, that's the critical value, times the standard deviation, which they told us was 2.3, divided by the square root of this sample size that we're trying to find. Okay, so algebraically, how do I go and find that? I would divide both sides by 1.96 first. So I have 0.5 over 1.96 equals 2.3 over root n. So the way I like to simplify this for people is to say if 20 divided by 10, we know that that's 2. Well, then it's also a true statement that 20 divided by 2 is 10. We can switch these two numbers, right? They're interchangeable, and you still have a true statement. So let's do that. Switch these two. Okay. So I would know now that root n is equal to 2.3 divided by 0.5 over 1.96. And then how do I go about solving for that? If I have a radical here, I square both sides. So I would have n equals 2.3. You can plug all this into your calculator all in one shot. Just square that whole thing. Okay. So what's that look like on the calculator? We have 2.3 divided by, and then another parentheses, 0.5 divided by 1.96. And then I just want to square that whole thing. So I get 81.2. Well, I can't sample 81.2 people. If I round this down to 81, then my margin of error is going to be bigger than 0.5, so I don't want to do that. Don't round this down. Even though it would round to 81, round it up to 82, always in that case. Okay, and you can see that in the lecture side. They get 81.29. Round it up to 82. We need a whole number for that. Okay. Okay, so in 6.2, we're still doing the same thing, confidence intervals for means, except we introduce what's called the t-distribution. So you calculate this t-value the same way you would a z-score. But when the sample size is small, like less than 30, and the standard deviation is unknown, we will use this t-distribution. Okay, I'll show you how this works. It's also in the appendix in the back of your textbook. But you can see, like, let's think about 95% confidence in this column, for example. We know in the normal distribution then that critical value is 1.96. Well, notice these critical values are bigger than 1.96. So because the sample sizes are smaller, we account for that by making larger standard deviations or standard errors, and it accounts for smaller sample sizes. So if I only have 12 degrees of freedom, which means I have a sample size of 13, the way that we calculate degrees freedom, you might want to make a note of this to yourself. I don't think because degrees freedom is, you know, for most applications we're going to do here, your degrees freedom is going to be sample size minus 1, n minus 1. Okay, so the same will be true for chi-squared when we get to that. That's a family of distributions that lives off these degrees freedom. So keep in mind that that's going to be n minus 1 for us. And then I'll show you now how we would use that t-distribution. So depending on the sample size, 95% confidence won't always be 1.96. That's what happens. Okay, so here's an example. We have a sample size of 15, so we would look at 14 degrees of freedom. We'd come down here to this yellow highlighted column. If I want 95% confidence, I can go to this column that lists level of confidence. That makes my life easier. Or I think about, remember we did this earlier, 95% confidence means you have 2.5% in the tail. So the table that you have in the back of your book does make this easy for you because it lists the level of confidence up at the top. You don't, when we're doing confidence intervals, you're not going to have to think about what's in the tail. But we should know, like 90% confidence means that you've got 5% in the tail, right? 95%, 2.5%. If you forget it, it's all right here. Okay. So that's our crash course to t-distribution. So if I wanted 95% confident, my t critical value would be 2.145, right? And that's how I would use that for my margin of error. We can also use the calculator for this, right? If I know that I have 14 degrees freedom and I want 95% confidence, right? How would I get this? I would inverse t 0.975 and then tell the calculator I have 14 degrees of freedom. So right by inverse norm is your inverse t. You tell the calculator, I know it's 95% confident, but remember that's 97.5 under the table. You have to add the tail in. And we should get the same decimal that we got off the paper, right? 2.145. Yay. 2.145. Okay. So what does this look like constructing a confidence interval for mean with the t-distribution? Right, so let's do one. We got 16 coffee shops. That's our sample size. We measure the temperature of coffee sold at each. The sample mean is 162. And the sample standard deviation, notice it's not saying population standard deviation, of 10. Construct a 95% confidence interval for the population mean temperature of coffee sold. So we go to stat and test again. And like I said, we're going to be living on this menu here. So we had the z interval previously. Now we have t interval. If the population standard deviation is unknown, we are making a t interval. Okay. So what was our sample mean in this one? 162 and a standard deviation of 10. Notice that asks for sample standard deviation. The menu looks a little bit different. When you do the z interval, it asks you for sigma right away. That's kind of the giveaway. And I think it was 16 different coffee shops. And let me refresh with my 95% confidence. And we go from 156.7 to 167.3. Let's see how we did. So they're doing all the nuts and bolts here, but that's what we want to get to, 156.7, 167.3. So confidence intervals for means, when the population standard deviation is unknown, that's your 6.2. Okay. Next we look at, still recording, good. Next we look at the confidence interval for proportions. So this formula looks a little bit different, but the nice thing about it is it takes us back to the z distribution. So we don't have to use the intricacies of that t distribution or finding those. We just have our point estimate for p hat. Okay, and we build our confidence interval around that. So your confidence interval formula is going to look like this. We have p hat plus or minus this margin of error. So let's take a look at what this confidence interval is going to look like in practice if we're going to, and we also have the sample size computation deal with this. Okay. So from example 1, construct a 95% confidence interval for the population proportion of U.S. adults who use Facebook. So our point estimate was 0.68. Okay. They told us that it was 68%. That was our point estimate. Let me just go back to example 1 so I can see if they gave us the actual number. Yep. Yeah, 1,054 out of 1,550. That's where the 68% comes from, right? 1,054 out of 1,550. So on the calculator, this is stat test again, but you may have to hunt around a little bit to find the one proportion z interval. Okay, so there's my one proportion z interval. Again, go back and look at what they told you your sample statistics were. Nope. 1,054 out of 1,550. So we have 1,054 out of 1,550. And we know that that was 68%. And I believe we do want a 95% confidence interval here. Yep, 95%. So we leave that alone and we calculate. So I get 0.657 to 0.703. And it should be the same thing they get. Okay, so they're calculating, compartmentalizing, finding the margin of error separately. We can do it either way. All right, and I want to find the example of so here you have a 99% confidence interval, but look what they give you for 18 to 29-year-olds who get their news on television. So we're looking at this 27% number. So this is a little bit different, right? I have a sample of 800. Okay, so when I go to stat and test, and I find that one proportion z test again, I don't want you to get confused when they give you the estimate as a decimal. Okay, so remember what you need. You need to know what x was. Well, they're not telling me x here. They're saying it's 27% of 800. So go ahead and calculate that. 0.27 times 800. Okay, and now what you want to be careful of, now that's worked out nicely for us. It's a whole number, but I think on the homework video you'll see if this is a decimal, then you're going to have to round it to the nearest whole number. Don't use the rounding up every time like I do when I'm calculating sample size. It's not what you're doing here. This was 216 out of 800, and now they want 99% confidence. All right, so I have 0.22957, 0.301. Let's see how we did when they work this out. Yeah, 0.23 to 0.31. Yeah, 0.23, 0.31. Okay. And then the last example that I want to make sure we're okay with is that algebra, finding the minimum sample size. So again, if you want, just go ahead and plug into the formula here if that's easier, or you can use the algebra, right? So the minimum sample size is going to be p hat times q hat, the confidence level, critical value over margin of error squared. They're going to give you all of this. You're solving for n. Okay, so if no preliminary estimate is available, we use 0.5 and 0.5. Okay, if they give us a preliminary estimate, then we'll use that for our p hat and our q hat. Okay, so we plug in 0.5 times 0.5. This is the formula. 0.5 times 0.5, 1.96 over 0.03 squared. They told us they want the margin of error to be no more than 3%. So that's where the 0.03 comes from. Okay. If they give us a preliminary estimate, here they give us a preliminary estimate, 0.31. So how does that change the game? You just use, instead of 0.5 and 0.5, it's 0.31 times 0.69. 1 minus 0.31. Okay? And then always round up. Always round up when you're finding that sample size. Okay? Don't hear me wrong and say that you're always rounding up for everything, right? Generally, you round to the nearest whole number, depending on the context. But when you're finding the minimum sample size, you're always going to have to round it up, because otherwise you're going to compromise that margin of error. Okay, and then the last part is a little bit different here when we get into estimating means and estimating variances and standard deviations. We have to look at a whole new distribution. It's called the chi-squared distribution. Okay, in your e-text, this is right next to, if you notice, if I just tap the page over from the t-distribution, the very next page, there's my chi-squared distribution. So you should notice right away it's not normal, it's skewed to the right. Okay? It doesn't follow the normal distribution, so we don't handle it exactly the same way. But we have these two particular values, the chi-squared left and the chi-squared right. So we have to know how to use that table to look those up. To find the actual chi-squared interval, okay, mildly confusing part of this, if you look at the formula here, for variance, right, that's standard deviation squared. It's real simple to get from variance to standard deviation. Just take the square root, not a big change. What you want to be careful of is this. You're going to look up a chi-squared right and a chi-squared left, but notice when they plug into this formula, chi-squared right is on the left part of the equation. Okay. Now, when you look up your chi-squared left and right, you still look them up to the left and to the right. So let me show you what I mean by that. So if I want 95% confidence and a sample size of 18, notice my degrees freedom is 17. Okay. How do I find these chi-squared lefts and chi-squared rights? We're going to go to the table and use it the same way that we had before, right? When I want 95% confidence, think about where I'm looking. I don't look in this 5% tail, right? There's 95% in the interval, so there's 2.5 in one tail, and the other area to the left is 0.975. If you have a paper copy of this, I used to write this out from show it to my students, but you put a 90% here and then just show that it links up with these two columns, right? 95%. 90%, what's 90% going to link up with? It's going to link up with this column and this column, right? Or I'm sorry, the 0.05 and the 95, right? This is your 80% here. These two are right next to each other. These two go together. Chi-squared left, chi-squared right. Chi-squared left, chi-squared right. And then you just build your way out. Chi-squared left, chi-squared right. You can kind of, you can just sort of match those up together. The chi-squared lefts and rights that match up. Let me see if I can. Sometimes when I write on my screen, it gets too messy. Okay, so what I was suggesting is that these two columns, that's your chi-squared left, chi-squared right, they match up. These two columns match up. These two columns match up, and so on. And then finally these two. So if you're trying to at 52.798 roughly, okay, and then I can just hit second to enter, and now we just go back and change that to our chi-squared right that we wanted. 13.121. Okay, so that's my confidence interval for the variance. You can see it right here. I want to look those chi-squareds up with you. Okay, so from 0.8 to 3.18, and that's what we got, 0.8 to 3.18. And then we just take the square root of both of those, right? To get the standard deviation, we take the square root of each of those. So they take the square root of the 0.8, we get 0.89, and the square root of the other value, we get 1.78. Okay.